Nevin is a computer scientist at Oregon working on a SYCL backend for the Cocos Performance Portability ecosystem. He's a C++ committee officer, vice chair, Library Evolution Working Group in Incubator, and representing Oregon in SYCL-related standardizations efforts as well. So during the talk, if you have questions, you're more than welcome to unmute yourself and ask questions, or simply just ask the questions in the chat and I will interrupt Nevin and ask questions. Nevin, thank you so much for being with us today. Please take away.
Sorry for the lowercase y. My autocorrect does that. I didn't notice it till just now, but SYCL's all caps, although it's not an acronym. Wait, so what I do at Argonne, I mean, there's kind of like three primary things. I'm working on the SYCL DPC backend for Cocos, and this is because this is what we're initially targeting for Aurora. I'm also the SYCL committee representative in the Kronos meetings, and on the C++ committee, and I've been doing C++ committee work for about a decade. I'm now the vice chair of the Library Evolution Working Group Incubator. Part of this talk, I've made two assumptions. Hopefully they're okay. Is that you have some familiarity with SYCL 121 and some familiarity with C++ 17. I'm not expecting expert level. And I'm gonna new features that we're using. I'm going to try to explain from both those things, from SYCL 2020 and from C++ 17, and even a little bit of C++ 20. So what is SYCL? I mean, this is just like the 1 minute. What is SYCL? I mean, it's an open standard published by the Kronos group, and it's for parallel computing and for heterogeneous computing, basically multiple devices under one roof. It could be CPUs, GPUs, and for us it'll be GPUs, DSPs, FPGAs. It's pretty general. Kind of the standard SYCL marketing slide that we have. A bunch of things feed into the SYCL compiler, the CPU compiler, and then go to a bunch of different backends. And so a question that comes up and is why don't we just use plain C++ for everything? Because C++ does support parallel computing. There's we're coming up with executors, there's execution policies, there's algorithms, there's atomics. But the thing that C++ is missing, and the major piece, is that there's no notion of heterogeneous computing, of having multiple devices. There's not even a notion of multiple processes on a single device. Like shared memory across processes does not exist, and it's not part of the object model. And if we want to add those, I would like to someday see those in C++, but do so, it would very my nice, good estimate is it would take a decade and probably 2 decades to do it, because it's a really hard problem, and things put into the C++ standard we don't want to be obsolete. So coming up with a general model for all this stuff that's going to stand the test of time is really hard. So we have SYCL and C++. So how are the two related? So SYCL is where we develop the parallel and heterogeneous abstractions. But our long-term goal is to put many of these things into standard C++. And we also, as new standards come out, we adopt the features from those standards to make it easier to make SYCL codes. And we take features from other that were developed not for HPC but for other domains. Like we take advantage of class segment argument deduction. We take advantage of polymorphic lambdas. There's types like span and optional and variant that we also take advantage of. And so this is kind of like the other marketing slide. This is various kinds of hardware we can do. And this talk, I'm going to focus on DPC++ because this is what we're really using for Aurora. And so, okay, another question is, what's the relation between DPC++ and SYCL? Well, DPC++ is Intel's open source implementation of SYCL with their extensions. It's based on Clang, and it's the compiler we're going to be using for Aurora. And it gives Intel also a place to explore and prototype new features they want to put into SYCL, right? Like SYCL wants to put things in C++, standard, DPC++ wants to put things into SYCL, right? That's the migration path. SYCL 2020 was released to the public on February 9th. It's called SYCL 2020 because when we we finished our version of it and gave it to the Kronos board to approve in December of 2020. So that's how we got the year name. We've moved the baseline. So in SYCL 121, the baseline was C++11. We are now at C++17, and we plan to be roughly one standard before the release one is what we want to be the baseline for time going on. One of the big things is we're moving away from being OpenCL centric. It started with under OpenCL, and like there's things, images and graphics processing. You can see that's where it started, but it turns out it's also can be very applicable to HPC concerns. It's like a little minor thing, like the include file is changing. It used to be CL/SYCL.hpp. Now it's just SYCL/SYCL.hpp. And the namespace, everything used to be under CL namespace CL SYCL. We're now moving it into namespace SYCL. And there's like over 40 new features. I can't get into all of them, obviously. Well, I picked 6 to talk about. Like the first 3 are kind of just like really big major things, major changes. They're all changes. Device copyable is sometimes implementation detail, but it's good to know what that's about because it can affect how you write things. And then the last 2, unnamed lambdas and deduction guides. That's things we've adopted from 17 and 14. Unnamed lambdas, probably more like started in C++14, and things we've adopted to make it easier to program in SYCL. The first big one is Unified Shared Memory, USM for short. This is a pointer-based model, and it's kind of a unified virtual address space across all the devices in the host. And if you allocate a pointer, it has the same value in terms of object representation on the host and on the device, which means you can just copy it anywhere. You may not be able to dereference it and access it, and there are restrictions there. But there's no translation that has to happen to the bits. You just copy the bits, and it just works. And there are 3 different allocation types. There's a device, you can do a device allocation, and that directly allocates in device memory. The host cannot access that. You would have to explicitly copy it back to the host if you wanted it. There's host memory, that's stuff on the host, and it is accessible on the device, although it may not be that fast. It may have to go over a bus. And there's shared, and the intention of shared is that it migrates between the host and device depending on where it's needed. Again, this is in one big virtual address space. And so, as I said, device allocations are, again, memory that's just for the device. The host can't access it. And there are special memcopy calls that let you copy it back if the host needs access to it. Host allocations, again, like I said, device access may be slower because it has to go over a bus like PCI Express. So it's kind of the intention for it is for things, either rarely accessed data or like large data sets that can't fit all on the device at once. There's shared allocations, which are implicitly accessible on both the host and device. And again, the data can migrate if on demand. However, it's not required to migrate. So, a conforming implementation of SYCL can just do the same thing and do it over a bus to give you access to it. There's also a prefetch call if you want to say, well, okay, I've allocated this memory and I'm going to use it on a device. So you say, tell the device, you call prefetch so that the device can first, start going to the device. By the time you actually need to use the data, it's there. There's also memadvise, which you can say, yeah, okay, I need this after this kernel runs. I'll need it back on the host, those kinds of things. But that's very implementation dependent, so you'd have to look at the actual compiler documentation to see what you pass the memory device. It's basically an integer you pass to it, and it's implementation defining what that means. This came up recently at Argonne. Allocations belong to what's called a context, which represents a device or set of devices, and like a queue has a context associated with it. And allocations are not usable across contexts. And this can matter because you may have multiple queues, and you would have to like allocate them based on or access your data based on where the allocation is, because the allocation functions take a queue or a context to allocate from. And if you have device allocations, they belong to a specific device.
Nevin, we have a question.
Sure.
So Leo is asking, why does SYCL allow the device to access host memory? Shouldn't we simply use shared memory for this purpose? I may have missed the design consideration behind this.
You may, yeah, if you have a large data set or something that's rarely accessed, you don't want to necessarily migrate it. You may just need a little piece of it. You want to migrate whole pages of it over. So it's slower, but it can give you access to bigger memory than you would get from you're sharing, right? It's on demand, and things may have to get paged out. That's usually that's the envisioned difference for the two. I mean, it remains to be seen how we're going to use it, but because this is a new feature. But that's what I would say the main difference is between those two. For rarely accessed data or very large data sets, the host can have lots of memory, and the device does not. That answers the question.
I believe so. There is another one. So it says, who does the copy in and out of the data and at which granularity?
Okay. So there. I was getting. It's basically you can explicitly do it yourself. There's special memcopy calls to say I want. Oh, for copying data or just migrating the data, like automatic access. If it's automatically accessed, the compiler will generate the code to get it for you. For shared allocations and host allocations, the compiler will generate code to get you the data at that address. If you want to explicitly copy the data, you can with the special memcopy calls for that, and that gives you fine-grained control of exactly where the data goes. Most of the stuff is implicit. Either if it's host memory data sent over the bus, or if it's shared, the pages are automatically migrated or using prefetch and memadvise. And what happens with on demand.
Thanks.
Did that answer the question?
I believe so, yes.
And there's like different allocation styles. There's kind of C calls, or there's a malloc call, and there's an align malloc. There's malloc host, malloc device, malloc shared, aligned host, a bunch. Those, like in C, right? You specify everything. You specify the size. There's also a C++ version, a template that returns a type pointer, and you just tell it how many elements you need for your array of them. You don't have to worry about the size of it. And then finally, there are stateful C++17 allocators. So if you wanted to put this in a vector and have a standard vector, and you want a standard vector to manage this for you, you could just use the stateful allocator for that. The one caveat about using allocators with things, I believe, because of the way vector works, it will zero out the memory, and you may not want to pay that cost. The main two differences. So what USM gives us is something very close to regular C++ programming. I mean, it's just pointers. Accessors give you something a little higher, kind of a little higher level, because it explicitly builds a data dependency graph between kernels. I need to read this thing after the previous kernel wrote it, and optimizations to take advantage of that. You want to do that with pointers. There are ways to do it. You can keep track of the events yourself, but you have to do that very explicitly and very manually. So a lot of it, which style to use, depends on what your code looks like already. And I think that's it about USM pointers. Yes. Any more questions on this?
Yes.
Ah, good.
So there is a question that Michael is asking, like, can you control then the NUMA domain host data? Can you control then the NUMA domain host data will be allocated from?
Not from SYCL. I don't know if lower level stuff will let you do that. I'm just not sure. But not directly from SYCL. It doesn't provide that abstraction. An API might provide that, but I haven't looked. An API is kind of the lower level beneath DPC++, beneath the SYCL layer that Intel's also providing for this. Which had a better answer.
Thanks, Navin. I think that's good. Thank you.
I can if you send me an email, I can find out. But that's questions I can't answer now. I can certainly get answers to. Moving on to parallel reductions. So this is the example of what a reduction looks like. Put in this slide in these slides. So if you look at reduction here, these are actually functions that return a reduction object. And when those are passed in parallel 4, those create reducers. Right? You pass these reduction objects into parallel 4, and then into the body of the parallel 4, and then the kernel. There are these reducers, which are also unspecified types. And in part of this, you also have three parameters, right? So you have the sum buff and max buff. Those are the reduction variables. Those were the buffers that were declared up here. The context. You have what the function is, right? Either plus is standard plus in this case, in the standard library, and all it does is it's a function object that calls, plus on the left and right hand sides of what you pass to it. And the maximum is just for expository. Basically, you want to get the maximum value of something that you're going through. It's just for also an optional identity. And the whole reason, because we don't know what types these return, is why we're using auto here, because they're unspecified, and they're basically it's a different type depending on what parameters you pass in. We pass this to parallel 4. We passing some reduction. It knows that in the kernel call we need a reducer object sum, and for max reduction we're going to need a reducer object max. And so we use auto here. And what the auto, this is a C++ 14 feature they're called generic or polymorphic lambdas. Right? Lambdas showed up in C++ closures in C++ 11, and then polymorphic ones showed up in C++ 14. And what that all that means is that this is basically it's a templated, can take any type, and generates code based on the types it takes. Now, what we really need is we only need one, right? Because we don't want to specify the types. And this is the only real way to do this in C++. Without having to spell out the type name, is use auto. Auto always gives you an exact type match. Just like template engines always give you an exact type match. Yeah, so you have these reduction variables, and you just pass them to parallel 4, and it magically does the right thing. Reducer objects, again, they look like this. Again, the actual type is unspecified. It's up to the compiler or the library to give you what it is. They're not copyable. They're not movable. And the only way to update the value they hold is with combine. And that's for one dimension one. So things greater than 0 dimensions, there's an operator square bracket that lets you work your way down to one. Basically, if its dimension was 3, it would create a proxy for one with dimension 2 and a proxy for one with dimension 1 until you finally get to combine, which lets you view to the final result. And for known binary operations, there are some synonyms given for combine. I'll get to that on the next slide.
Nevin, we have another question.
Sure.
So Leo is asking for reduction. Can we use a different intermediate type, different from the input-output types?
I mean, you can specify what type it's going to be, but you don't really have control over how it's being contributed. This is generated for you, so I don't think you can. It's let's go back to it. Right. It's generated from sum buff and max buff. Right. It knows that's the type. It knows that's what you want to store it in, and it knows what the identity is for that, or you can pass on a different identity if you needed to. Believe that you have to use that type. There's no intermediate space anywhere else to put things. Right. It internally knows what the types are. There's no way to specify it that I know of. I'd have to look to make sure though. Downside of presenting is I can't just go look. Like other telecoms, I usually just have, I can, look for things as these kinds of questions come up.
Thanks, Nevin.
Oh, yeah, so so reducers are pretty simple, and you can also get the identity out of a reducer if identity value is known. And what the implementation will guarantee is that it's safe to call combine concurrently from different work groups, different work items. The reduction variable will have the result when the kernel finishes executing. You're given that. If you pass multiple reducers like we do in this example, you don't know the order between them. Right? There's no guaranteed ordering for when things get updated. As I was saying, like if you look at sum, it uses sum plus equals input values IDX. That's the same as you could also said sum dot combine input values IDX, just like max dot combine down here. Because sum uses standard plus, we just for convenience we can add an operator plus equals. And if t is any kind of integral type for plus, we also add plus plus, which just adds 1 to it if you're just trying to increment something. And there's synonyms for standard multiply, standard bit and, standard bit or, standard bit exclusive or there will be. I mean, this is the intent. Turns out, as I was looking all this stuff up for the presentation, I found a bug in the SYCL 2020 standard. There are two forms for standard plus. There's standard plus that takes a type in the middle, and then there's standard plus avoid, which is defaulted. So standard plus angle bracket is standard plus avoid. And we don't actually specify for standard plus void that the synonym should be there, but that's certainly the intention. All the examples show it, and we certainly want to do that. So when I'm done with this talk, I have a pull request to make to the spec. Hopefully that gives you a flavor for how reductions are working in SYCL 2020. Any other questions on them?
So there is a discussion sort of going on in the chat. So Leo is talking, so it wouldn't work out of the box if I need a norm, complex numbers, and one real numbers out. And I think Jaming is responding that for integer sum, it may be good that input type is integer while output type is long. And then I guess there is another question that it says, suppose I have a multi-threaded pthreads or OMP SYCL code. Can I have different threading issuing commands on to the different or the same queue?
Well, no, that's not. No offhand, I'm just not in that mindset right now. Threading issues on queues.
Okay. The other question is, how would these reduction objects different from SYCL atomic underscore reference reductions?
Know what cycloatomic reference reductions are? Is that just a previous version? I mean, this interface is morphed. This interface even morphed since, I believe since the SYCL 2020 provisional spec that came out last year. We go on during the design, for instance, instead of just parallel 4, like I think it was CGH that reduce when you wanted a reduction. So we've certainly changed what the interface should be. I don't know what the other one is. I'd have to see it.
Okay. Yeah, people are so excited. They're just
No,
asking
they're good. They're
questions
good
ahead of
questions.
time.
They're good questions. It's big. I mean, SYCL's a big topic. I'm trying to become an expert in all of it, but it takes a long time.
Yeah. Okay, so if
I
there are
work.
no
I
more,
work in Cocoa's backend, so I'm not. I'm directly using SYCL, but in weird ways that application developers aren't directly using it the same way.
yeah, I totally agree. So let's continue.
Okay. Next thing is how atomics have morphed. So in 1.2.1, they were modeled on the C++11 atomic class, and they only supported relaxed atomics, unlike C++11, because of OpenCL, because OpenCL only supported relaxed atomics. And the thing about the C++11 atomic class and the SYCL atomic class is that they own the data. And it turns out, we figured out over the years that that's an overconstraint, because you may say want atomic access only some of the time, and then okay, I'm done in my kernel. I don't need atomic access in my host. I want regular optimizations to happen. But if it's a type, there's no way to say that. There's never a way to non-atomically access it. And again, this makes sense for the C++11 timeframe when all this stuff came out, because there was really no notion of non-owning interfaces to things. I mean, the best we had at the time was, raw pointers would be non-owning by convention. And it's still kind of that, and people are not happy with that. They want this in the type system. There are things like observer pointer, for instance, that have been proposed to put this in the type system. Although you still have to support raw pointers. And like canonical example for this is interfaces with strings. Like you may have a function A that takes a standard string, and it also takes a pointer and a size, because you don't want to force everybody to put everything into a standard string, because that might do an allocation. Along comes it took us about like 5 years, yeah, about 5 or 6 years to get string view in, and that is the first view, the first non-owning reference to data. And it's basically not just string data. Internally, it's just a pointer and a size, so it's efficient to copy around. And it turns out it makes a great vocabulary type for interfaces. I know when I first saw string view, it was called string ref at the time. It was proposed by Jeffrey Askin at Google. I go, that solves a lot of the problems I had, because I used to, before working at HPC, I worked at a trading firm on high frequency trading, and I didn't want to do string allocation. This is back before strings were um, string optimization, so they always were doing allocations, and I didn't want that. And I go like, why didn't I think of this? Because it seems like that's a really simple solution to this problem. Is that if I have an interface that's not owning, that solves a lot of problems, and it gives you a separation of concerns, right? Because we only care about the operations performed. We don't actually care about how the data behind it is managed. And this is all the rage in C++. So in C++20, we added atomic ref, which of course I'll get more into. And there's a new type called span, which is also important to HPC, which is a non-owning reference to contiguous data. It's in some ways it's like string view, right? It's if it's dynamic, it's a pointer and a size. If you know the size at compile time, it's just a pointer internally. And ranges have a bunch of also non-owning interfaces. And again, in C++23, I say maybe because I mean we're still standardizing it. Function ref is again a non-owning interface to do function calls, whether it's a function object or a function pointer, and MD span, so multidimensional span. Those two things are coming. Hopefully, we can get them both in C++23. But again, until we actually ship a standard, no guarantees. So more about atomic ref. So this is again non-owning atomic access to data, right? The one in SYCL, right? And we're modeling it on the C++20 atomic ref class. And SYCL is only required to support relax, but it may also support acquire release and sequentially consistent semantics. So these are kind of the main differences between the two. One I want to point out is T. So the types you can pass in into standard atomic ref, they have to be trivially copyable. The SYCL ones are more restricted. It's kind of it's the list down there, and unsigned int, long, unsigned long, long, unsigned long, float, and double. Specifically, there is no support for large types, things like complex double. And to support those kinds of things might require some globally accessible lock table, and we just so far are not supporting that. Also, two more template parameters. The next one is memory order. We instead of so C++ standard ones has the default as being safe, so they just say, okay, we're going to default all our parameters to sequentially consistent because that's the safest one for people to use. For SYCL's purposes, relax is probably would be a better default, but this way we don't even specify it. You just, when you instantiate the template, you say what the default order you want. So for our use case, this is more general and more useful than sequentially consistent. And then just kind of a detail here, like if you say that you're using acquire release, right? The read order you'd want to be acquire, the write order you'd want to be default to release. And also in each of the function calls, even if you have the template where you say what the default values are, you can override them in the functions themselves. The load can override the memory order and the memory scope. Memory scope is basically memory order constraints. You can say it's, this is atomic with respect to work items, subgroups, work groups, device, or the system. Template parameters, sorry about that. And then there's an address space. You can say is a generic space or global space or local space, and defaults to generic. And performance tuning, if you make it more restrictive, you make it better performance. Oh yeah, basically, yeah. To recap, is this is modeled on C++20's atomic ref class, and changes to make it more useful for SYCL. Questions about that?
We have a quick question that is asking about how is large type defined for a slide 37?
It's uh, basically the only types, in SYCL, the types are listed. The only types supported are integer, unsigned int. If it's not one of those types, it's not supported under your SYCL atomic ref. Even if you have those like sitting in a struct, like you have a struct with one integer type, that is not supported right now by SYCL atomic ref. So large type's kind of a misnomer. It's really, if it's not in that type list that's right there, it's not supported. And I mean, personally, I think this is, something I'll likely push for. We want to support things like complex double. That's kind of useful to have atomic access to. But that would, be a proposal, and we have to get it through the SYCL committee. And if you have use cases for that, let me know. I mean, having actual use cases is a much easier sell. Saying we need this feature. We don't want to just develop features in a vacuum. We want to, solve actual problems. I'm going to go on to device copyable. this is in a lot of ways has been the bane of my existence. I've been doing trivially copyable issues for a while, and you think it'd be a simple subject. It's not. So how do we copy objects in C++, right? Normally we call a copy constructor, copy assignment operator, but that can involve running code, and that code may access both the source data and the destination data. Right? It's arbitrary code. It can do whatever it wants. So how would that apply to things like inter-device copying? Right? I want to copy from a host to a device or between two devices. Well, if I have a non-trivial copy constructor or copy assignment operator, and I'll define what trivial means in a bit, like then it has to run code. Where would that code run? Does it run on the host, on the device? And what happens if it's a device allocation? You can't legally access in both places. Right? So about all we can really do is copy the bytes, which is the object representation, to make up the object. In C++, right, we have a thing called trivially copyable types. And we kind of use that as a proxy for types where we can copy the bytes. And its definition is morphed over the years. Basically, all the virtual base classes, all base classes and non-static members must be themselves trivially copyable. That's kind of the recursive part. It must have at least one public non-deleted copy, move, constructor, or assignment operator. This is for to handle corner cases. Like if your type, for instance, has a constant member, then it would not be assignable, even though it is copy constructible. So it has to have at least one of these. And for any of those that it has, those must be public and defaulted. And it must have a public defaulted destructor that does no work. And conflated into trivially copyable, what compilers have done is both the notion of bitwise copyable, and some compilers make layout decisions based on whether or not something is trivially copyable. And because of this, and these other restrictions, it's too restrictive. And it's not necessary, and it's not even sufficient to say, even if I can copy it, whether or not I can use those objects on the device, right? For instance, member functions can throw arbitrary exceptions, and you can't do on a single device. And plus, there are historical reasons why some things are not necessarily trivially copyable. Pair and tuple are the obvious examples. Even if pair contains types that are trivially copyable, pair itself is not in tuple implementations. And we can't just ask vendors to change that, because that breaks the application binary interface, an ABI break. It may change layout, because layout's conflated in there. It may change what it looks like, which would break a bunch of code out there. It's kind of, I don't want to say unwritten, but it's like ABI does not appear in the C++ standard anywhere, yet it's something that the committee takes very seriously, and vendors have almost a veto power if it's we're going to arbitrarily break ABIs. Then there's also some new types. 20 span comes, and 17 basic string view, that are not guaranteed to be trivially copyable yet. Although I have a paper, 2051, to make those things trivially copyable, and it just passed the first hurdle. So by 23, those will very likely both be trivially copyable. And all the major implementations of those two, again, they're just a pointer and possibly a size. There's not much to them. The internal guts of what they have. They're already trivially copyable in all the major vendors. I don't know of any vendors where those are not trivially copyable types now. What's the problem with all this? The lambda, right? So we use lambdas all over the place, and they capture things, right? We use equals to capture everything I'm going to, a copy of everything I'm going to need. The lambda captures a non-trivially copyable type. A lambda, again, it's just a struct. That lambda itself is not trivially copyable, which means if you want to use it, for your kernel, you can't implicitly copy it to the kernel and just run it. The compiler will complain. And we noticed both Kokos and Raja, when implementing this stuff, we both came up with this. And what we end up doing is we end up manually copying the bytes to the device, or to device memory. But that's also got a problem, because that technically violates the C++ object model. C++ is very concerned about the lifetime of objects. does an object get created? When does it get destroyed? And optimizers make decisions based on that. And even if optimizers today aren't making decisions based on that, they can and will in the future. And we don't want code to just break in the future. Because it's technically, if you violate the object model, this is undefined behavior. Launch the missiles is the joke usually, but anything can happen. So, I know this notion of device copyable, and we use this. We want this to be able to say types where bitwise copying for inter-device copying has the correct semantics. And it's unspecified whether or not the copy move constructor or assignment operator is called to do the copying, because it may not be able to, right? If it's copying from a host to a device, there's nowhere to run the code. And it's unspecified for the same reason whether or not the destructor is called on a device, because the effect of the destructor has no effect. Users can specialize this trait to indicate that a type is device copyable, but you're doing that at your own risk, right? When you do that, you are asserting to the compiler that this is a type where bitwise copying has correct semantics. That assertion is wrong. This is a bug. This is undefined behavior and a bug, and it could be a hard to find bug. And again, it may not be a bug today, but a compiler later in the future could be optimizing based on that. The name of the trait we finally settled on is device copyable. It defaults as trivially copyable, and it's specialized for standard array, standard pair, tuple, optional, and variant when they all contain device copyable types. And the reason this is needed is right now, if you have an array, optional, variant of trivially copyable types, then they themselves are trivially copyable. And we would like that same behavior for any type that kind of is a collection of those kinds of things, which those are. But we don't have things like reflection yet, so we don't have an easy way or a good way other than hacking the compiler, modifying a compiler to do that. So this is the best compromise we have right now, is that we specialize those types to say, okay, if they have something that's device copyable, all device copyable types, then it itself is device copyable. And we need that recursive, we want ultimately that recursive definition. This is about the best we can do, is by saying these are the types where this matters. And it's also right now specialized for span and basic string view, because those are not guaranteed to be trivially copyable yet. So it's kind of like, it looks like a little detail, but it's a detail that matters. And especially if you have your own object, if you're making your own object for a kernel and you try to pass it, and you get a weird compiler error, think about, is my type trivially copyable? Are those semantics correct? Right? Because if you run into it, the errors you get from compilers are not great. That this just basically, you get like an error like this just didn't work. Questions on this? Now I'm going to move into more usability kind of things. So unnamed lambdas is a feature we got. So over here, right, this is a regular, SYCL 121 parallel 4 kind of code, and you have to name the kernel. And it turns out, so the model behind SYCL is that the front end is just plain C++ code, even if it does something different. So the code should just be, should be C++, even if it's going to be interpreted differently. And it turns out this thing is a weird, but it's valid C++ syntax. And what it does is, if the kernel name has not been seen before for a class or struct, then it's a forward declaration of a function local class of the function that encompasses this line of code. It's a very weird thing. And this is required, for SYCL 121. You have to name every kernel. And the big reason for that was you needed a unique global name for tool chains that had a separate device compiler. If you're doing like multipass with different compilers, because there isn't one for lambdas. A unique name. There's no guarantee. SYCL 2020. 2020, we got rid of the need to specify it. If it's one tool chain, the compiler generates a unique name. I mean, you may wish to specify it when you're debugging, but it's certainly not required. Get out, right? Simplify your code. This is a really simple feature, but it makes things, much easier to use. You don't have it, you don't have that weird class kernel name thing in there, which is just, people go, what does that mean, right? Because it's just weird. And that's the shortest part of my talk on Unnamed Lambdas. Finally, deduction guides. So what a deduction guide is back before C++ 17, right? If you wanted to pair double, you would write it like this, right? Initialize it. And it turns out we added what's called deduction guides. Is you don't have to, you can deduce the template parameters for type from its arguments. You have no need to specify them when declaring non-member variables, right? You can just say standard pair p2, 3. Now, one rule is all parameters must be deduced. You can't do like partial templates. And there are ones implicitly generated by the compiler. I think like standard lockguard, for instance, has implicit ones. Although if you want to use, you don't have to, right? So I didn't put that example up here. Lockguard takes a mutex as a template parameter. The type of mutex is a template parameter. You do no longer have to specify that at all. You can just say standard lockguard, lock, paren, mux for mutex. Oh, I've noticed under client there is a warning you might have to turn off if you have a bunch of warnings turned on to say that you meant to do this because it's an implicitly generated by the compiler. And then there are user-defined ones, and here's like pair for some corner case reasons has a user-defined one, and they're very simple, right? It says if I see a construction of the form, pair, type 1 and type 2, I want it to map to this template for pair instantiation. Again, it means I can throw that out, and again, the one downside to this is that if you're actually storing these things in structs and classes yourself, not with like lambdas, if you actually use all the template parameters, you can't just say standard pair. There's no syntax for automatically generating this. I mean, I suppose you could use decal type if you really tried, but so for SYCL 2020, we put a bunch of user-defined deduction guides. ID, vector, buffer, multi-pointer, range now has them. And for instance, here's the ones that we added for ID. You notice these are not templates themselves. It says if I have an ID and I pass one parameter, well, I really meant ID1, right? If I pass two parameters, I really meant ID2, right? If I pass three parameters, I really meant ID3. And now, one place where we had a lot of template stuff is accessors, and there was no way to do that. So what we did is we added what are called TAD constructors for accessors. Tag is just usually an empty type, a templated. Usually you declare a tag, and you declare a variable of that type so we can pass it by name. And the tag typically looks like this. It's just a struct. It has an explicit default constructor, and what this does in C++ is that you have to call it with a name. You can't just call it with open curly, close curly syntax, right? Normally you could, because if you just said struct tag t and there was nothing in there, then that's an aggregate, and you can call it with that syntax because you can initialize any aggregate. It's an aggregate of 0 members. And then usually you declare a variable of that type. Inline context is also 17. Inline is a 17 feature. It's like inline functions that you can declare it in multiple compilation units, and there's only one exists. It's very useful. If we have code like this, right, you have a buffer with a range 2, and you can just say, oh, I have an accessor that's going to be write only, the property no init. And what write only is, it turns out write only is variable defined by SYCL. And DPC++, its actual type is mode tag t tag type of this template primitive, access mode write. And there's a deduction guide that we'll call it of this constructor at the very bottom. right? So the top part of this is the complicated declaration for accessor, the template parameters, and how they get defaulted. And then there's a new constructor in there that takes a tag. And if you didn't have that, the actual type of this thing of accessor is really accessor of int2, access mode right, target device, access placeholder true. That's a lot to type. It's a lot to keep track of, and those are details most people don't care about, right? You just want an accessor that's write only. So it makes code much easier, much easier to write and much easier to read, unless, of course, you actually need those types because you want to store them somewhere in a struct. Bonus CTAD here. We also have the range call, but since range also now has deduction guides, you can get rid of the two. The first two, sorry. Get rid of the two in the angle brackets, I should say. So deduction guides are, for me personally, I thought deduction guides is one of the flagship features of CSL 17, especially the explicit ones. The implicit ones, the rules are complicated, so it's sometimes hard to figure out what'll happen, except in the easiest of cases. But certainly explicit ones, I think, are just well worth having. Any questions? Because that's pretty much the end. We still, build information examples and modify them from, these are kind of the 4 resources I use, like specification. The current one up there is revision 3. Well, it's weird if you Google it, it says revision 2 in the Google link, but if you actually get it, it's revision 3. There's a book that the Intel folks written. I have right here. I can't show it very easily. Data Parallel C++ by those authors. It's really good. If you want to understand the concepts behind things, it's the book. Read the book. Go to the specification when you need actual detail. If you need certain details about things. But if you want to just a really good understanding, the book's really good. And on the web, there's a SYCL Tech, which is like all things SYCL, links to like everything going on. People doing blog posts, things that just come out. And Kronos also has a blog, although it's more kind of general for everything in Kronos, not just SYCL. And that's my talk.
Thank you, Nevin. That was a very good, informative talk, and there was a lot of good discussion going on. So I would like to let the attendees know that we will be sending the slides after the call. I see a question. So can we use DPC++ for host compute only in case there are no accelerators?
Yes.
Yes. This is meant to be a
one code. It's turning out that was a requirement in SYCL 1.2.1 that's becoming more optional in SYCL 2020, but yes, you can. There may be systems out there that don't really have a host.
Yeah. Okay, so we have another question. Do we need to use range for the accessor in your last example, just like V1, 2, and 3?
No, there's a bunch of different constructors, and basically we added a bunch of tag ones. There's a bunch of new constructors for accessor, so it's all the regular accessor constructors, plus there's a bunch of new ones. Right.
Okay.
This is just one example of many.
Okay, another question is, does DPC++ support virtual functions on the device? If not, is there any plan to do so?
It's not yet. We're talking about it. We'd like to. It would likely be an optional feature because things like FPGAs can't really support that kind of thing, and SYCL's supposed to. But yeah, we would we would like that. If you have use cases why you need that, that would be good. What usually comes up when this gets discussed is, why can't you use something like standard variant, right? So standard variant, you basically give it a list of types that all the types that it could possibly be, and you have use cases where either it's too hard to rewrite it using standard variant or you don't know all the types. We would like to know because they'll certainly help the arguments for getting virtual functions.
Another question is, do you think it's more efficient to use USM or buffers accessors?
I don't have performance right now, numbers right now. So I just don't know how to answer that. I can't really answer that question yet. I mean, it's a lot of it is, I mean, if you're starting from scratch, do you need, the dependency graph? Use accessors. If you want your code to be more C++ and C-ish, pointers they're just much easier.
Another question is concurrent kernels supported?
Believe so, yes. You would just submit to different queues.
Okay. How is performance compared to pure OpenMP from a mature compiler?
But we're still developing for Aurora. I do not have performance numbers as part of this.
Yeah, that's a very tricky question because I mean even for the
Yeah.
OpenMP there is still compiler is like
Yeah. So
getting better and better. So yeah.
when I was at Apple, they gave us a great answer for this. It's like, I will be delighted not to answer your question.
Um, okay, so another question is there something analogous to CUDA pinned memory in SYCL?
Not really. I don't know. Could have. I barely know it, so I can't really answer. I'm not a good person to answer that question. I don't think so. From what I understand of it.
Another question is, can I get a smart pointer from a USM allocation?
Yes, I mean you can, because again you can use allocators, so you can, but you can't necessarily pass. For instance, you can't pass a shared pointer into a kernel because those are reference counted. So to pass it would require running code to update the reference count. So you can, like, you might want to, store it, like, even like store something in a unique pointer, but you still need the raw pointer when passing it around. That trivially copyable, like, the restriction is it's a tough one. I admit, but we don't know a better solution for that problem at this time.
Okay, so there is another question. Are there any plans to allow, I'm assuming this is direct manipulating the SYCL DAG in upcoming release or DPC++ extensions, for example, creating external